Welcome to this explainer. Okay, today we are going to decode the math that is absolutely powering the next decade of Web3. We're talking about a technology that honestly sounds like science fiction, but it's already processing billions of dollars in transactions right now. It's called the Zero Knowledge Proof, or ZKP for short. Okay, let's dive straight into this. How do you prove you know a secret without revealing what that secret actually is? I know, it sounds like an impossible premise, right? Kind of a total paradox. But this exact question is the foundation of a cryptographic breakthrough that is literally reshaping how we think about the internet, our data, and trust. To get why this is such a game changer, we have to look at the massive problem blockchains are facing right now. Look, blockchains are public ledgers. That's their greatest strength when it comes to auditing, sure, but it is an absolute nightmare for privacy. I mean, imagine if your bank account was just broadcasted to the entire world. Your salary, your everyday trades, maybe your somewhat embarrassing NFT bids, all of it visible forever. For years, the default answer was just, well, don't use crypto if you want privacy. But that completely breaks any potential for real mainstream adoption. Enter zero knowledge proofs. And hey, I want to set your mind at ease right off the bat with a great quote from our source material. ZK looks like magic until someone explains the trick. You absolutely do not need a PhD in cryptography to understand this. Throughout this explainer, we are going to reveal the magic trick behind the math, step by step. Let's start with the famous cave analogy. So picture a cave shaped like a circle, with just one entrance. The path splits left and right, and it meets at a locked doorway way in the back. Now that door needs a password. You claim you know the password, and I want you to prove it to me, but you flat out refuse to tell me what it is. Okay. Here is the protocol. You go into the cave and pick the left or right path completely at random. I wait outside where I can't see you. Then I shout, come out the left side or come out the right side. Now, if you truly know that password, you can unlock the back door and exit the correct side 100% of the time. But if you don't know it, you're stuck. You only have a 50-50 chance of guessing which side I'm going to shout. Now, here is where the math really kicks in. If we repeated this test 20 times and you exited correctly all 20 times, the chance that you're actually lying drops to 1 in a million. So how does this build into the formal definition of a zero-knowledge proof? Well, the cave analogy brilliantly illustrates the 3 absolute requirements of ZK. First up, completeness. This means if the statement is true, the verifier is convinced. Second, soundness. If the statement is false, the prover will fail the test. And third, zero knowledge. The verifier learns absolutely nothing about the secret itself, only that the prover actually knows it. It's fascinating because the math mirrors that physical cave analogy perfectly. Now, before we go any further, we really need to bust a few common myths. Here is what ZK is not. First off, it is not encryption. Encryption hides data, whereas ZK proves facts about data. Big difference. Second, it's not privacy by default. A ZK network can actually be completely public, like ZK Sync, where the word ZK just means proof without reveal. And lastly, it's not actually magic. There's a massive asymmetry going on here. The prover does a huge amount of computational work to generate the proof, while the verifier does just a tiny amount of work to check it. So let's talk about that crucial asymmetry. Think about the number 300. To put that into perspective in a blockchain context, a prover can take 10,000 complex transactions, crunch all the math, and produce a tiny proof that is just 300 bytes large. The underlying Ethereum network can then verify that tiny 300-byte proof in about 5 milliseconds. It instantly knows all 10,000 transactions are correct without ever having to rerun them or, frankly, even see them. That right there is the incredible scaling power of ZK. All right, we've seen the trick. Now let's look at the equipment. Section 1, the magician's tools. SNARKs versus STARKs. Let's demystify these 2 main families of ZK proofs. Now, what's really interesting here is the direct trade-off between proof size and security. Think of SNARKs kind of like a feather. They're incredibly lightweight with those tiny 200-byte proofs and extremely fast to verify on Ethereum. But they do have a vulnerability. They require this trusted setup ceremony to generate public parameters, and they are not safe from future quantum computers. On the flip side, STARKs are more like an anvil. They're heavy, we're talking massive proofs up to 200 kilobytes, which means higher costs and slower verification on the main chain, but they are incredibly robust. They require zero trusted setup, making them fully transparent, and they're inherently quantum resistant. Because of these wild trade-offs, we've ended up with what cryptographers like to call the proving system zoo. It's pretty cool to see how the industry is experimenting.
We have Groth16 for the absolute smallest proofs, which Zcash uses. Then there's Plonk, which fixes the setup issue by making it universal. We also have pure STARKs being used by StarkNet. But here is where it gets super fascinating. The industry is actually converging on hybrid models, like Plunky 2. Polygon uses this to get the best of both worlds. They do all the heavy proving using a scalable Stark, and then wrap that up in a tiny SNARK so it's super cheap to verify on Ethereum.
So we have this incredible mathematical primitive and literally $10 billion of R&D investment behind it. Let's move to Section 2, the grand illusion, focusing on real-world applications. The difference between types of rollups really brilliantly illustrates why ZK is widely considered the endgame for scaling Ethereum natively. Traditional, optimistic rollups definitely scale the network, but they rely heavily on trust and game theory. They post the data and basically say, hey, trust me, this is valid. That requires a 7-day challenge window where anyone can flag fraud, meaning if you want your money out, you're waiting a whole week. ZK rollups, on the other hand, rely on pure math. They post the data along with a cryptographic proof. The network checks the math, and boom, finality in 10 minutes. No agonizing wait times, no trusting strangers. Just absolute mathematical certainty. But ZK isn't just for scaling transactions. The sheer versatility of this tech is mind-blowing. Think about your identity. Right now, to pass KYC, you're sending photos of your actual passport to dozens of different apps. That creates massive data honeypots just waiting to be hacked. With ZK, an issuer verifies your passport exactly once. From then on, you can mathematically prove to an app that you are over 18 without ever revealing your actual birthday. You could prove your credit score meets a certain threshold without handing over your entire loan history. And looking ahead, we have ZKML, which stands for Zero Knowledge Machine Learning. With that, you can prove an AI model ran correctly and produced an output without revealing the proprietary model or any of the private input data. This brings us to a highly sensitive, but honestly crucial application, the regulatory bridge. Right now, there is a massive clash between crypto's desire for privacy and regulators' very real need for anti-money laundering compliance. We saw this play out when the mixing service Tornado Cash was sanctioned. But Zero Knowledge actually offers a technological bridge here. It allows for what's called selective disclosure. Basically, you can mathematically prove to an auditor or a decentralized app that your funds did not come from a sanctioned hack without having to completely dox your entire financial history to the public. It's a way to actually bridge privacy and compliance. Now, I know this all sounds incredibly powerful, and it for sure is. But as an explainer, we really have to look at the full picture. We need to pause the hype for a second and ask a tough question. What are the actual limits of this magic? What bottlenecks is the technology currently facing today? Let's break down the strings attached to ZK. First off, for SNARKs, those trusted setups are a real risk. If the secret data used to set up the network, often called the toxic waste, isn't properly destroyed, a bad actor could literally mint infinite fake proofs without anyone ever knowing. Second is data availability. ZK proves a transaction happened correctly, but it doesn't store the transaction data itself. You still have to pay to store that on the main chain. Third, the user experience is definitely lagging. Generating a ZK proof right now on a mobile phone can take around 10 seconds and absolutely drain your battery. And finally, privacy isn't automatic. Adding privacy to a ZK network requires extra engineering and extra circuits, which simply costs more money to run. And hey, speaking of costs, here is a pretty sobering number, $50. Today, generating a proof for a batch of 10,000 transactions costs about $50 in cloud computing fees, and it requires massive servers with 128 gigabytes of RAM. Because of this steep cost, only a few centralized operators, known as sequencers, can actually afford to run the network right now. We're heavily relying on massive leaps in hardware, things like dedicated GPUs and ASICs over the next 2 to 3 years to drive that cost down to just a penny and truly decentralize the proving process. When you step back, zero-knowledge proofs are arguably the most important crypto technology since the blockchain itself. Look, they're not magic. They are rigorous math, incredible engineering, and they come with very real trade-offs. But they offer something totally unprecedented: scale without trust and privacy without hiding. So I'll leave you with this to think about. As this technology matures and the hardware catches up, if we can finally prove facts without revealing our underlying data, what part of the internet will zero-knowledge transform next? Thanks so much for joining me for this explainer, and keep learning.